Hi everyone and welcome to our first video for topic 9. We're going to review in this video congruence and then examine a little bit of what correspondence is and what it has to do with congruence. So first off, let's talk about congruence. What does it mean for things to be congruent, right? So if you remember in the past, we talked about that things in geometry, objects are not the same as each other. They're not equal to each other. Even if I have two objects that seem to look a lot like each other, right? They're not the same object. In this case, they're two different objects, right? But they can be very similar, right? And that kind of connection is called congruence, not equality. Congruence is to geometric objects as equality is to numbers. So for example, their side lengths can be equal, right? And their angle measures can be equal. But the actual objects are not equal, right? The objects are congruent. Same shape, same size. So when we talk about same shape, what do we mean by shape, right? Consider this. If I was to make, say, a square, right? I could consider that a shape, and then I can make something that has the same side lengths, right? But is a different shape. All I've done is lean the square over. So just the side lengths, right? Just the actual perimeter of the object, that's not enough. They can't just be the same side lengths. It needs to have the same shape. Shape is determined by the angles, the vertices, right? The things that make it do the weird, making a star versus a pentagon versus a heptagon or whatever. The number of sides, and not just that, because again, these both have four sides, but the angles at which the sides meet. That is shape, right? On the other hand, you can have size. For example, I can make a little square and I can make a very big square. These are the same shape, but they're not congruent because they're not the same size. Here, the side lengths are very obviously different. So to have congruence, they need to be the same shape and the same size, right? Now, when we were talking about congruence in the past, we kind of first started really examining it with rigid transformations, right? What was special about rigid transformations? What were the rigid transformations? Well, those were things like translation, where I slide it over, right? And that's all I did. They were things like rotation, where I rotate it around and I end up with it pointing a different direction. And they were things like reflection, right? Where I reflect the object over this line and it looks like that, right? And I can make that even clearer even if I use a shape that's not as symmetrical. For example, this one would become this one, right? Those are the three rigid transformations. And what made those special is that the image and the pre-image, in other words, the shape after the transformation and the shape before the transformation, right? Those are congruent to each other. Now, we had very briefly talked about a special word when we said this, which was that they are mapping onto each other, that they correspond. And what did we mean by that? Correspondence. We've seen it now with rigid transformations, and we've seen it now with corresponding angles. So let's break down what is correspondence. Correspondence are pairs of things in math that are matched together. And essentially, if I give you one, you know the other. It's not a coincidence that correspondence is a word in math, and outside of math is used to refer to like letters and mail. I'm sending correspondence to you, or we're corresponding, right? Now, you can also think of correspondences in like, Victorian or Elizabethan romance, where it's like, oh, my dearest Darcy, I was so touched to receive your intimate correspondence. I do feel we are soulmates. It's about matching. It's about connecting. More specifically, it's about mapping, right? Earlier we said there was a mapping when we did rigid transformations, which is if I give you one point of the rigid transformation, say, for example, I'm going to reflect this, right? I map it because the reflection, every point has an image on the other end, a prime, that is its mapped corresponding point, right? The B and the A flipped because it's a reflection, and so B prime is corresponding to B because the reflection flipped them. So it's not just, where they are, left, right, or up. It's specifically which one goes to the other one. If I give you B and I say this is a reflection, across a vertical line, you will know where to find B prime. That is what makes correspondence special. If I give you one, you know the other, right? It's essentially like giving you the return address and the delivery address, right? If I give you one, you've given the address, you know where to take the letter to drop it off at B prime. That's why they share the word with mail, right? It tells you where to go, okay? Using correspondence and congruence, right, we can see why rigid transformations are corresponding, right? And when I do this, they line up. Congruence has to check not just the side lengths, not just the angles, but both, right? Because side lengths tell us size and the angles tell us the shape. And when we transform one onto the other, right? For example, this one and this one, I can see that these angles match up with each other, right? They correspond, and that confirms to me that their shape is the same. And then I would check their side lengths and see their side lengths match up and line up with each other after the reflection, which tells me that they are the same size, and that tells me that it is a congruent relationship. So when we're checking if things are congruent, a good way to do it is to use a rigid transformation, because rigid transformations only work if the image and preimage are congruent. So I can take my shape and I can, slide it, then reflect it, or slide it, then rotate it, and see, does everything line up after I do that? All right. Now, using this, we're going to examine how to show that triangles are congruent and what the definition of a congruent triangle is. We'll also talk about why we're worrying about triangles in particular. So I'll see you then.